So the extreme value theorem. The extreme value of functions is essentially a way to guarantee in mathematics that you have an absolute max or min on a interval. So we will often refer to the extreme value theorem function in calculus as EVT. So we have IVT for intermediate value, EVT for extreme value. Our goals for today are to be able to algebraically find absolute max and mins, as well as local, and all of them are going to use the extreme value theorem. So if you have an absolute maximum value on a domain D, then we can say that there is some f of x less than or equal to that f of c for all of the x values in D. So again, that's that absolute. That means that there is the highest point on the graph and there are no points higher than it. And that highest point occurs at C. So the highest point on the graph is at x equals c. F of c represents the height of that highest point. So it means all the other y values are less than. Converse, same is true for the absolute. So it means that f of c is the absolute lowest point and all the y values are greater than it. So we like to talk about trig in Calc. So we have y equals the sine of x. So we know that the sine of x function is oscillating. It repeats over time. We know that its domain is on one cycle is 0 to 2 pi. Its domain in all the world is all reals. And then that its range on a normal untransformed one is -1 to 1. And all the other values occur in between. So if we only want to look at the curve from 0 to pi, get your key points in there. At 0, 0. So when sine is 0, it's at 0. Sine of pi is also at 0. And then in between 0 and pi is pi halves. Pi halves represents 90 degrees. The sine of pi halves or the sine of 90 is 1. So the sine function increases from 0 to pi halves, hence it is always positive, and then decreases from pi halves to pi. So in that quadrant, though, my y values are still positive. So if we sketch that curve, what could we say about sine on that restricted domain? If the domain is limited to just 0 and pi, does that graph have a max? And if so, where? Yeah, it has a max. It has a max at pi halves 1. That max is also an absolute max. There are no values that are ever going to be greater than. Do I have an absolute min? So this is where it gets a little tricky. The two lowest points are at the same lowest points. So therefore it is an absolute min, which is tricky. But because they are both at 0, then you have two absolute mins. Because the absolute minimum is with respect to the y value. So if it said, do you have an absolute min? The answer is yeah, I have an absolute min at y equals 0. That is the lowest point. It's just that it occurs twice. at understanding what that statement kind of says. So then what we want to do is we want to investigate what you can do to a domain to change your answers. So as of right now, we have x squared plus 2. The domain of x squared plus 2 is all reals. Does that have an absolute max or an absolute min? So does this function, as it stands now, have an absolute max? No. Does it have an absolute min? Yes. Because if you follow that rule, at x equals 0, y is going to be 2. There are no y values less than 2 ever on that graph. So there is an absolute min at y equals 2 that occurs when x is 0. What happens if I take that domain and I shrink it? So now I don't want my domain to be 0 to 2 or negative infinity to infinity. I want to make it 0 to 2, including 0 and 2. So that's the difference. It includes the endpoints. So now, I want my graph to go from 0 to 2, including 0 and 2. Does that graph have an absolute max now? The answer is yes, because at 2, the graph has reached a maximum height. At 2, because the graph is increasing from 0 to 2, including 0 and 2, at 2, we've reached our highest peak. So now I have an absolute max and an absolute min because I have a restricted domain. So the absolute max is at x equals 2. So 2 squared is 4. 4 plus 2 is 6. So my absolute max is at 6 when x equals 2. My absolute min hasn't changed. It's still at 2 when x is 0. What happens if I decide to no longer include? Zero. What happens now? Do I have an absolute max? Do I have an absolute min? No, because it gets infinitely close to that point, but never gets there. What about if neither endpoint are included? So now again, none. Because in that open interval, there's not a point that is higher or lower than any other point. That brings us to the extreme value theorem. So again, on your page, I kind of like showed you all of the zoomed in on a different version. Just to kind of help. But The extreme value theorem is very specific. It says if you have a continuous, oh, we left that word in Calc, function, now it has to be a closed interval. EVT only applies if two of those things occur. It has to be both continuous and closed. On that interval, then F has both an absolute max and an absolute min. It is guaranteed if you have a closed continuous function that you will have a max and a min that are absolutes every single time. If you do not have that closed interval, or if you have other critical points that occur in that closed interval, then we can refer to these as locals. So again, seeing those graphs from earlier, we know that a local occurs if a function is increasing or decreasing without bound. So locals can occur, but they occur in what we call open intervals that are increasing or decreasing without bound. You will often hear me call our max and mins extremas. So by calling it an extrema, it leaves it open-ended that I don't necessarily have to call it a max or a min. When we find these algebraically in calculus, we're going to start by calling them an extrema because at first it's a critical point and we don't know whether that critical point is a max or a min. So the extrema is the easiest way to label it. So now that we've increased our vocab, increased our terminology, we have a better understanding. Going to another graph, how would you label all of those pieces now? So now you want to make sure you include the word local. So local max, local min, absolute max, absolute min, taking into account that this is a closed interval. It is a closed interval. So that means this point here has a closed endpoint. It's not increasing without bound. So we have an absolute max at -1, and whatever you kind of think that y value is. 36, I should say. Then you have a local min at 0, 0. You have another local max at 1. You have an absolute min over at 3 and a local max at 4. So again, absolute at x equals -1, local at x equals 0, local max at x equals 1, absolute min at x equals 3, and a local max at x equals 4. When you don't really know your y values, you can identify them as x's. So at this point, you've heard me say the word critical point, but we haven't formally defined the word critical point. All of those values I just gave you are referred to as critical points. Critical points are extremas of a graph. They are also zeros of a derivative. So a critical point is an extrema of a graph that occurs on the interior, meaning in that domain of the function. And if you were to find your derivative is going to be 0 or DNE. So a DNE case would be if you had like an absolute value. So we know that the minimum or the maximum of an absolute value is a point that is a sharp corner. So we know that we can't find those derivatives because it's so steep on the left and so steep on the right that the slopes don't match. So in that case, you would have at a critical point, it would be an extrema, but it would be non-differential. So critical points are zeros or DNEs of the derivatives. The extreme value theorem allows us to find the absolute critical point, but it also gives us the locals. So we're going to go to tomorrow, we're going to talk about something called the candidates test. The candidates test is a way of taking all the critical points, putting them into a table to determine which is the absolute or which is, a local. So today we're going to just start by identifying them. And like I said, tomorrow we're going to transition away from identifying and looking at them and turning them into a table. A more efficient way. So we have f of x equals 3x to the fourth minus 6x cubed plus x squared. So looking at this, is this an even or an odd function? Even. So that tells me that this graph is only going to go up. It's not increasing without bound. It is increasing indefinitely. However, what did I do to it? I restricted it to -1 to 4. So we're taking a snapshot of the entire picture. We just talked about critical points and where they occur. The critical points are the points that can be the extremas. So what do I want to do? I want to find my derivative, and then I want to find where it is 0 or DNE. So we find our derivative, we set that derivative equal to 0. For my sanity, I'm going to take out a 12x. Making my interior numbers a lot smaller, it gives me a nice quadratic. It is cubic, so I'm looking for 3 values at which this is going to be 0. The first value is at 0 itself. The second value is going to occur at the zeros of the quadratic. So if factorable, which this one is. Then you set those factors equal to 0, and we get 0, 1, and 3. Then you go back to your restricted domain, and you say, okay, are all of these critical points in my domain? And at this point, unfortunately, they are. So that doesn't allow you to eliminate any of them. So what we have to do now is that quote-unquote candidates test. We need to look at the critical points as well as, and go back to that x squared plus 2 example, the max, the absolute max, and absolute min on that x squared plus 2 with that restricted domain. The absolute max and min occurred at the endpoints. So my mnemonic device for EVT is that EVT says you have to check the endpoints. The endpoints are the interval points. So bring on that candidates test. You're going to check your endpoints. And your critical points. The endpoints and the critical points are going to be checked in the original function. So you need to take the original y values. So for me, if I'm doing this by hand, to find those critical points of the original, I take out an x squared. Because what it does is help shrink down my numbers. So like -1 squared is easy, it's just 1, so that kind of eliminates. So now it's just taking 3 times -1 plus 16 plus 18. So 16 and 18 is 34. 34 minus 3 is 31. When I do it again, 0 is my favorite by taking out the x squared. 0 times anything is always 0. So, boom. One squared is 1, so that one's pretty easy. And then 3 minus 16 plus 18. So 3 plus 18 is 21. 21 minus 16 is 11. 11 minus 6 is 5. 3 squared is 9. 3 squared is 9. 9 times 3 is 27. Plus 18 minus 48. So 18 and 48 is going to be a nice -30. 27 minus 30 is -3. 9 times -3 is -27. So like, just going back to elementary math and grouping it is kind of what I do to try to do the math mentally. So instead of like taking 27 and 18 and adding them, which I could have done, and still would work, I just try to make my numbers a little smaller and then go from there. Or I look at like matching 8s. Unless we're about 4. 4 squared is 16. 16 times 3, we already know is 48. 16 times 4 64 plus 18. So 48 plus 18, 58 plus 6 is 66. So 66 minus 64 is 2. 32. So what you should notice is that one of my critical points is an absolute, but one of my endpoints is an absolute. So that's why it's so important to check your endpoints, and it should make sense. Like that 4 is the absolute. What do you know about that even function, right? I said it increases indefinitely. So even though you have all those critical points, remember something to the fourth kind of looks like the W. So like here's your critical points inside that W. Well, yeah, it should make sense then that 4 is greater than 3 and even 1 because this graph is going up forever and ever and ever. So this is my absolute max. And then this is my absolute min. -1 would be, and 0 and 1 would all serve as locals. They would be like local max and mins, but they're not absolutes. So what we're trying to do is identify the absolutes for EBT. Okay, this time we have x cubed minus 3x squared plus 1, closed interval. So same thing, find your derivative. Set your derivative equal to 0. At this point, we haven't had any points where it's a critical point yet that is a DNE because we don't have that absolute value or we don't have a denominator. DNEs are going to come in from the denominators a lot of times. I've given you nice differentiable polynomials to start. So take out a 3x, leave yourself with x minus 2. Therefore, my critical points are at 0 and at 2. So then you apply that candidate's test. So we're going to say, okay, where are the absolutes? The absolutes are going to occur at the highest y value. So you need to take into account both the endpoints and any critical point that occurs between them. So again, I just kind of take my numbers off to the side, plug them in, go from there. So, absolute max at 417, absolute min at 2 negative 3. EBT says endpoints. I cannot stress that enough. EVT means you have to check your endpoints as well as the critical points. Endpoints, critical points, candidates test. That's what it's often referred to. So like if you were to like leave here and like go check somewhere else, or you look in our textbook, it's called the candidates test. Because these are all candidates of potential absolutes. And then you get to the crazy, not so fun functions, and this is where being really good at the quotient rule comes into play, because now we have f of x equals 1 over the square root of 4 minus x squared. This is not a just restricted domain, so we are not guaranteed an absolute. However, the function in itself has a restricted domain. So we know that you can never A, have a denominator equal to 0, and B, you can never have a negative under a square root. So we need to determine what is our domain. What is our domain? So the domain is going to come from the fact that 4 minus x squared must be greater than 0. And again, because it is in the denominator, it is not equal to 0. If that square root was up top, then it could equal 0. But it can't because it's in the denominator. So again, we talked about these at the beginning of the year. You can't just move over that x squared because it's either going to occur inside the grid points or outside those zeros. So again, this is kind of like 2 minus x, 2 plus x. We know that the roots or the zeros are at plus or minus 2, but you need to determine, does it live inside or outside plus or minus 2? So if I plug in something greater than 2, like 3, 3 squared is 9, 4 minus 9 is negative. Negative 3 is going to be the same. 0 does work. So what that means is that this function or graph exists between negative 2 and 2. My domain lives inside this one. If the x squared and the 4 were flip-flopped, it would have lived outside. Now that we know our domain, is that an open or a closed domain? It is open. So does EVT apply to this function? No. So don't justify your reasoning with EVT. Can this graph have extremas? Yes, but they're not justified by EVT. They are not guaranteed as absolutes, and you cannot check your endpoints. So find your derivative. You have 2 choices for this. You can do the quotient rule, or you can bring the square root up as a negative and do the chain rule. How many of us would bring our square root up? How many of us would have just automatically done the quotient rule because you weren't thinking? So you get O, D high, and here's where the quotient rule and like everything ends up canceling anyways, because this zeroes out. Minus high, no, and you end up doing that chain rule with that negative square root anyways. Just have to do this is a first large. So chain rule says 1/2, keep the inside, take 1 away, times derivative of the inside, which is negative 2x, all over denominator squared. So that's 4 minus x squared, because the square root and the square cancel. Cleaning this up, your negative times a negative turns to a positive. Your 1/2 and your 2 cancel. So now you have x times negative square root, or times the square root of 4 minus x squared, that is a negative. So you have x over the square root all over this, multiplied by your reciprocal. So that brings that up, and you get x over, ready for this nifty thing? So this is the square root, right? You know that the square root is really the 1/2 power. So a half times a whole is 3/2. So that's square root times that is 3/2. Now I know many of you said you would not have brought that up as a negative. Had you brought that up as a negative, you would actually very easily have seen that. So if you had made this 4 minus x squared to the negative 1/2, your rule is bring the power down in front. Take 1 away, so a half minus 1 is negative 3/2 times derivative of the inside. And again, negatives cancel, 2's cancel. Here's your x. Negative exponent drops to the bottom. That's why it's so, like, you can see how less messy this is. It's so critical that if you can apply those rules of bringing the power up, knowing when you can algebraically do something, this is so much easier than the closure rule. Closure rule killed my space on it. However, that still leads us to the whole main point of the problem, which is to find the critical points. So my critical points are those zeros and DNEs. So I need to find the zeros, which occur when the top is equal to 0. So you get x equals 0. So the function is equal to 0 at x equals 0. What do we know about x equals 0? That's in my domain. So we are happy. That is a critical point. It's valid. The DNE critical points occur when the denominator equals 0. So this is the critical point when f prime of x equals 0. Now I need the critical points when f prime of x does not exist. And it does not exist when the derivative of the denominator is equal to 0. So if you want to get rid of the 3/2 power, you multiply it by its reciprocal power, which is 2/3. So we're going to take this to the 2/3, which means we take 0 to the 2/3. But we know that anything to the 2/3 power is, or 0 to the 2/3 power is still just 0. Now you just solve for x squared. So now you move your x squared over, you get 4 equals x squared, which means the critical points of the denominator are at plus or minus 2. But what do we know about plus or minus 2? They are not in my domain. So these critical points get tossed away because they are not in my domain. So how many critical points does this graph have? It has 1. That one critical point then is going to be either a max or a min, and then we can prove if that critical point is an absolute by proving if the function is increasing on one side and decreasing on the other. So now you would take that 0, plug it back into the original. So you get 1/2. Again, that 1/2 is not guaranteed to us to be a max or a min, because we don't know if it is increasing or decreasing around it. So this goes back to what we did before with the 0 being on our number line and comparing its f prime values. So you compare -1 and +1 inside the derivative, not the original. So we know that inside a square root has to always come out positive, because otherwise you can't take your square root. So the denominator of the derivative is always positive. So if the numerator is negative, then the graph is negative. If the numerator is positive, then the graph is positive. So that tells me that this graph is decreasing, then increasing. So 0 is what type of extrema? 0 is a min. So it goes from decrease to increase. Okay. We can find extremas on piecewise. So you can still do the same process. Find your derivative. So what do we know about this function and its derivatives? Are they going to match? No. So technically, if it asks you is f prime differentiable at x equals 1, your answer would be, because the slope from the left is -4, the slope from the right is 1, so they're not differentiable at x equals 1. So what happens is when they don't match, that derivative loses its point. So you start assuming it is there, but then once it's not there, you can take it away. Okay. And we also know they're not continuous if you plug one into the originals. Will we have any critical points? So what you do is you take those graphs and you say, okay, -4x has to equal 0 and 1 has to equal 0. Because those are my derivatives. So the critical points occur at the zeros. So we get x equals 0. Well, that's not in that's in my other domain, so I can check that critical point. So because this is a piecewise and we have a singular critical point, and it's not continuous, we know that local max or mins can occur at its endpoints now. So for the candidates test of a piecewise, you have to do your critical points as well as your two endpoints just to determine if either of those are mins or maxes. So you have your critical points and your endpoints. So what that looks like, if you were actually to go and like give yourself a rough sketch of this. So on the left part of that piecewise, you have what? We have a local max. You don't have local mins at those endpoints because they don't match up, or your local max at those endpoints because you cannot talk about what's happening to the left or to the right of it. So you have a local max at 0. Pause for there.